All right, welcome back. Chapter 4, Section 1.2, Finite and Algebraic Extensions. Now that we have the notion of vector space and dimension all set up, we can do all sorts of neat things. So let's start with the definition. So first of all, when you have one field sitting inside the other, we call the smaller field a subfield of the big field, and the bigger field an extension field. Part 2 of the definition is much more important, and we're going to use it a lot to control things. So when you have f sitting in K inside of K as a subfield, we'll say that K is a finite extension if its dimension as vector space over f is finite. And we will call that dimension the degree of the extension. And we're going to write it with this notation here, the brackets K and the colon and the F. So for us, most of the interesting fields and subfields and extensions that we'll be looking at will be finite extensions. And we're going to be able to say a great deal about them. If it's not a finite extension, of course, we call it an infinite extension. As our first example, of course, the real numbers sit inside the complex numbers. This is, as we saw last time, a finite extension. The dimension is 2, so we say that it's a degree 2, that C is a degree 2 extension of the reals. For our next example, Q sits inside Q attached root 2. And also we saw this was a degree 2 extension. The dimension was 2. And therefore it's a finite extension. And for our third example, Q sits inside the real numbers. And it is an infinite extension. It has to be infinite. It's an argument by contradiction. If there was a basis, a finite basis, then you could write every vector in R as a finite linear combination of Q, and that would mean that R would be countable. But it's not, and so it's an infinite extension. All right, next, another definition. Okay, so to begin with, start with F contained in K subfields, and S any subset of K. We'll write F with square brackets around S, F of S, to be the ring generated by F and S inside of K. So this is just as a ring, so we've actually seen this before. It's just different notation. We used to write this with the pointy brackets, and it would just be F union S generated as a ring. All right, so we've seen this type of construction a few times now. We'll write F with round brackets, F of S, to be the way we think of it, and this is actually a fair definition if you set things up properly, to be the smallest subfield in K that contains F and S. So square brackets are it's the smallest ring that contains F and S. Round brackets, the smallest subfield that contains F and S. Rather than making this definition precise, though it's easy, we're going to do it in the usual way. So the official definition will be the intersection of all the subfields in K that contain F and S, as usual. It's easy. You'll do it in your homework, that you get a field this way, that everything is well defined. That's all straightforward, and you've seen this both in the group and in the ring setting already. Finally, we will say that F of S is a simple field, a simple extension of F, if there's only one element that you've added. And more generally, we'll say it's finitely generated if I've only added a finite number of things to F to get F of S. All right, for an example, and once you look at this example, you'll have a really good feel of how all these things fit together. We're going to look at the case when S has one element, alpha. So this would be an example of a simple extension. So we already know how to handle rings. So this is just a review with slightly different language. F square brackets of alpha would be the set of all linear combinations of powers of alpha. So that'd be the sum of all sums, ci alpha to the I, where each of the coefficients is in the base field f. Now, so just as a remark, if you have, alpha satisfying some polynomial equation, then many of these terms are unnecessary because they'll be zero. So, as a more specific example of our example, if I do q squared bracket attach the root square root of 2 sitting inside the real numbers, then since the square root of 2 is rational, all those even powers of square root of 2 can be absorbed into the first term, the I equals to 0 term. And all the odd powers can be factored out as a single square root of 2 times a rational. And so all you really need is just a plus b square root of 2, and that gives the whole ring generated by square root of 2. All right, now let's look at what happens when we go up to f round brackets alpha. So this will be the smallest field containing f and alpha. It's simple to show in your homework that this will just, in this case, be the ring that it generates with all the inverses thrown in. So let's write this out. So here it is. It's just all linear combinations of powers of alpha with coefficients in f times the inverse of the same thing, all linear combinations of powers of alpha. It's really easy to see that this is indeed a field, and it's also trivial to see it's the smallest field that you get. So let's look again now at that example of our example where we look at q attached to the root 2. Now we already know that for the numerator, so to speak, we only need a plus b root 2's. Same thing will go with the denominator. We only need sort of c plus d root 2's. However, all the denominators, you can do this trick you learned in, 5th grade or something about clearing square root of 2's in the denominator. You multiply by this stuff here, and the result is you get it in the numerator again, c minus d root 2 all over a rational number. And so we get the field generated by the square root of 2 is, in this case, the same as the ring generated by the square root of 2. And this is really phenomenal because the ring is way easier than the field. I mean, look how horrible this baloney is for the field, but how easy, the ring part is. Anyway, this is not an accident. This will happen a lot, and especially in the cases that we care about and are important. And that leads us to our next definition. All right, so an element U in an extension field K is algebraic over F if there's a polynomial, so an F in the ring f of x, so that f of u is 0. This is what happened with the square root of 2 in the previous case. It satisfied the equation x squared minus 2 is 0. And that, it's going to turn out, is what made things so nice, where the field that you get by attaching an element was the same as the ring that you get by attaching the element. If there's no polynomial that kills u, it's called transcendental. Transcendental elements are essentially, with probability 1 on the real line over q, everything is transcendental. Pi, e, almost anything you pick at random. However, math is rarely about completely picking something at random. So the ones that come up in a lot of applications, by and large, and maybe amazingly, are the algebraic ones. The transcendental ones are all kind of the same in some sense. There's some homework problems on it you can look at if you want. But the ones where we can make real mileage and say things that are really useful and eventually very deep have to do with algebraic elements. And part 2 of the definition, we say that K is an algebraic extension if every U in K is algebraic over F. Now at first it seems maybe as if this would be really hard, but again it actually is easy to satisfy and comes up a lot. Let's see, to that end, let me just remind you that k is finite over f, as we saw just a minute ago, if the degree of k over f, that's the dimension of k as a vector space over f, if that's finite. So what we'll see very soon is that if you're a finite extension, you're always algebraic. Soon we'll also see that when you attach a single element to a base field, then you get an algebraic, it's an algebraic element, if and only if what you get is a finite extension. So attaching algebraic things gives you finite, which means those extensions are always going to be algebraic. But we have to prove all that baloney, so let's start with a lemma. Okay, part 1 of the lemma. The degree of k over f is 1. It's a vector space of dimension 1. If and only if f is equal to k. All these statements in this lemma are going to be easy. We're going to leave them to read in the text or to do on your own. But if you have, saying dimension 1 just means, for instance, the identity element is going to be a basis, which means that all linear combinations of that with f coefficients is just f, and it's kind of clear then that you can work backwards and get that's the same as f is equal to k. Anyway, that's in the text. I'll let you read it. Number 2, if you start with an element in f, then, well, alpha is in f if and only if f adjoined alpha doesn't give you anything any bigger. If and only if the degree of f attached alpha over f is 1. That follows right away from number 2. All right, the last part of the lemma is that if you do successive attachment, first you attach alpha to f, f of alpha, and then you attach beta to f, f of alpha attach beta, then the field you get would just be the same as attaching f and alpha together to f. Again, that's straightforward. You've seen that stuff before, and we'll use this in later propositions. Our next theorem in some ways has, in terms of what it does, is kind of similar to Lagrange's result. Lagrange gave a strong combinatorial constraint on subgroups in that the order of H had to divide the order of G. We're now going to give a similar result, and it gives a constraint on subfields. All right, here's the theorem. It says if you have F contained in E, contained in K, all subfields of each other, or of the people to the right, then the degree of K over F is the same as the degree, if you want to go all the way from K to F, that degree, it's the product of the degree going from K to E and the degree going from E to F. And as a result, if you know the big dimension from K to F, then any subfield, these degrees in the middle have to divide that total dimension. So that's a big constraint. All right, let's turn to the proof. Let's write the dimension of K over E as M and the degree of E over F to be N. I'm going to assume both of these are finite. If either is infinite, it is simple to prove that, in fact, the dimension of K over F is infinite as well. I'm going to skip that. You can read it in the text, or maybe it's even a homework assignment. But anyway, let's work with the case where both of these are finite, and let's give names to the bases. So we'll write U sub I for the basis of K over E, and we'll write V sub J for the basis, a basis for E over F. So the claim is that if I look at all products, Ui times Vj, that I get a basis for K over F. If that's true, that will prove the theorem, because I'll have m choices here and n choices there, and so the order of this basis will be m times n, which is the statement of the theorem. So to prove that it's a basis, I need two things. I need to show that it spans and that they are independent. First of all, any element k in K can be written as a linear combination of Ci ui's. for some ci's in E. And this is because the ui's here were a basis for k over E. In particular, they span. But these coefficients ci, since they're in E, can be written as a linear combination of the dij, as some dij vj for some dij in F. And that's because the vj's span E over F. And if you combine these two statements here, then you see that you can write any k as a combination of ui vj's times coefficients in D. So that's exactly the statement that it spans. Okay, turn to independence. If I can write some linear combination of the ui vj's, the coefficients here we'll call dij, and get them to add up to 0, I want to show that all the dij's are 0 to get independence. However, the trick is just to reorder how we're adding things here. So group all the j's together. You can write this sum here in this form. And then notice that the d's are in F and the v's are in E. So this entire sum are coefficients that are in E. And what I've said here is that I've got a linear combination of the ui's with E coefficients adding up to 0. But because the ui's are a basis, that means that each of the coefficients have to be 0. So there it is written out. The sum, each of these coefficients, the sum of dij, vj, has to be 0. But now the vj's are a basis, and these coefficients are in F, and the vj's in particular are independent, so all those coefficients have to be 0. So that's the end of the proof. Since they're a basis, we're done. All right, this will be a very powerful theorem. We'll use it a lot. But eventually our goal is to understand the structure of all finite extensions. To that end, let's start with just adding a single element. In other words, we're going to start with studying simple extensions. Let's start with a lemma. All right, so the lemma says if you have F a subfield of K, and alpha is in K and algebraic over F, then there's a unique monic polynomial F in f of x, so that the ideal generated by F is the set of all polynomials that are killed by alpha. So it's the set of all g in f of x, so that g of alpha is equal to 0. Bear in mind, of course, the ideal generated by F consists of all the multiples of F. So all the multiples of F, FH's, where H is anything in f of x, that consists of all the polynomials that kill alpha. In addition, once you find this polynomial f, it's always true that it's irreducible in f of x. And we have a definition we're going to plop in here, even though we haven't quite finished proving this lemma yet, or even started it. But the f that you get here is called the minimal polynomial for alpha over f. And we'll say the degree of alpha over f is just the degree of this polynomial. Now, you've probably seen these in linear algebra when you were doing canonical forms, and you were looking at roots of the characteristic polynomial, and then you would find this minimal polynomial and do things with it to get the Jordan canonical form. Okay, so for the proof, let's let I be all the polynomials g that have alpha as a root. So all g so that g of alpha is equal to 0. It's trivially an ideal. Because f of x is a PID, there is a polynomial f so that the ideal generated by f is I. Okay, so we can take this polynomial, grab off the leading term there, multiply by the inverse. That, of course, won't change the ideal because we're just multiplying by a scalar. And by doing so, we may assume that f is monic. So this at least gives us the existence of this polynomial, monic polynomial that generates the ideal. For the uniqueness, we already know that all other generators for this ideal are associates of f. That means off by a non-zero scalar multiple. Unless you're multiplying by 1, that'll mess up f being monic. And therefore f is the unique generator of this ideal that is monic. Now, if f could be factored, in other words, if it were not irreducible, then you could write f as g times h, two other polynomials, and they'd each be of lower degree. Since alpha is a root of f, that means either g of alpha or h of alpha has to be 0. By relabeling, let's say g of alpha is 0. All right, so the problem is then if g is in I, since g of alpha is 0, it's in I, this is violating the fact that I is generated by f. Everything in I therefore has to have degree at least the degree of f. And so that's the contradiction because g was supposedly of lower degree. All right, that'll be the end of that lemma there. All right, let's turn to an example. Let's look at Q inside of C, and let's consider alpha to be the root 2. This is algebraic, since x squared minus 2 kills it. And in fact, I claim this guy is irreducible. All right, by Eisenstein's theorem. So it's irreducible, it's manifestly monic. And since it's irreducible, that means it has to be the generator of the ideal. So the minimal polynomial x squared minus 2 has degree 2, and so we say the degree of square root of 2 is 2 over the rational numbers. All right, now let's do a very handy theorem, one that we use a lot. It completely tells us how to handle and the structure of simple algebraic extensions. Okay, so setup. F is a subfield of K. Alpha in K is algebraic over F, and let's say F is its minimal polynomial and that it has degree n, so degree of alpha is n. First statement says the field you get by attaching alpha to capital F is the same as the ring you get by attaching alpha to capital F. And remember, as we've said, the ring is way easier to deal with. So the fact that you get the field by just attaching alpha as a ring is a great simplification. So f of round brackets alpha is f of square brackets alpha. Moreover, we even know what this field is isomorphic to in terms of a quotient of a polynomial ring. It's always isomorphic to the polynomial algebra f of x mod the ideal generated by f. Number 2, we can write down a basis for f of alpha over f. It's just all the powers of alpha, 1 alpha, alpha squared, up to alpha to the n minus 1. So in particular, we have n elements there, so the dimension is n. And so the degree of the extension, f of alpha over f, is the same as the degree of alpha. Okay, the last one is another of these combinatorial constraints. It says n has to divide the degree of k over f. So that is a very strong constraint on the degrees of these elements. All right, let's turn to the proof. All right, start with number 1. We're going to define a function phi sub alpha. It goes from the polynomial ring f of x to f attach alpha, okay, as a ring. We're just going to define it by phi of alpha applied to g is g of alpha. It's trivial that this is surjective. I mean, you can just use degree 0 stuff. And it's trivial to check that it's a homomorphism. Also, obviously, the kernel of phi of alpha is just the ideal of things that have alpha as a root, and as we've already said, that's the ideal generated by the minimal polynomial. Okay, so our first isomorphism theorem tells us that the ring f of alpha is therefore isomorphic to f of x mod f. Okay, but we can say more. Since f is irreducible, that means f is prime. That's because we're in a UFD. This tells us that the ideal generated by f is actually maximal. That's because we're in a PID. So that tells us that the right-hand side here, f of x mod f, is actually a field, which means f of the square brackets is a field. But this says the smallest field containing f and alpha, that's f of round brackets alpha, is contained in f of square brackets alpha because it's a field and has f and alpha. And since the ring generated by alpha is always contained in the field generated by alpha, in fact, the two are equal. And that's the end of part 1. Okay, so any g in the polynomial ring f of x by the division algorithm can be written as f times some quotient plus a remainder, where the degree of r is less than the degree of f. Apply phi alpha, and of course we get the ring generated by alpha. That's just all linear combinations of powers of alpha, so that's manifestly all the g of alphas, where g is in f of x. Right, g is fq plus r, but when you plug in alpha to f, you get 0. So that's the same as the set of all r of alphas, where the degree of r is less than n. It's clear that if you look at what this does, that this is just the span of all the powers of alpha from of power 0 all the way to power n minus 1. So as a result, the ring f of alpha is definitely spanned by all of these n elements. In fact, of course, we claim they're independent as well, so that they're the basis. Okay, so to show that these vectors are independent, suppose that there was a linear combination that added up to 0, so sum of ci alpha I adds up to 0. Well, then if you replace this alpha with x's here, then this polynomial, the sum of ci xi, is in the ideal generated by f. However, it's got lower degree than f. So the only thing with degree lower than f, the only thing in this ideal here with degree lower than f is the 0 vector. And to be the 0 polynomial, that means all the coefficients have to be 0. All right, so as we said, the degree has to be, the only thing in here that has lower degree is 0. The 0 polynomial has all 0 coefficients, so each of these ci's is 0, and that means that we get these vectors over here are independent, just as we wanted. Of course, this means that we have a basis, and the dimension is n. All right, for the last one, we simply just write down the following chain of subfields. All right, so by the multiplication of degrees, if you have f sitting inside f of alpha, sitting inside of k, this total degree here, k over f, is the product of these two smaller degrees. And in particular, k over f is this number here times the degree of f of alpha over f, which is n, which simply says that n, in fact, divides the degree of k over f. And that's the end of this proof. Okay, let's go ahead and draw a kind of corollary from this. I guess I'll call it a lemma, though. Okay, for f contained in k and alpha any element, then alpha will be algebraic over f exactly when, if and only if, the degree of f attach alpha over f is finite. All right, one direction's easy. If you're algebraic, then we've already seen from above that the degree of f of alpha over f is actually the degree of that minimal polynomial. And in particular, it's finite. So first of all, in the other direction, if the degree of f of alpha over f is n, then when you look at this collection of vectors, 1 alpha alpha squared, all the way up to alpha to the n, you've got n plus 1 vectors in there. So they have to be dependent. So that means you've got some ci's, not all 0, so that when you add up the sum of ci alpha I, you can get 0. In other words, there's a dependence relation. Okay, well, once you have that, then you're done, because then you just let f be the sum of ci x to the I with those same c's, and obviously it kills alpha, which means that alpha is algebraic. Okay, so when you're attaching a single element, being algebraic is the same thing as saying attaching it only gives you a finite extension. Okay, that completely tells us how to handle attaching a single element, and in terms of it being algebraic and dimensions and all the stuff like that. What we don't know yet is just a finite extension. Okay, so this next theorem is going to tell us how to handle general finite extensions, and we'll have a corollary, I guess, after that, and that'll be the end. Alrighty, start with f contained in k. Then the first statement says, if k is finite over f, then actually it's an algebraic extension. Okay, so all the elements in K are algebraic over F. I suppose I should note that, we have the arrow only going to the right, and that's because it's definitely, you just can't go to the left. There are algebraic extensions that are not finite extensions. But for most of the things we want to do, if you have finite, you get algebraic for free. Okay, part 2 gives us the if and only if. So your finite extension over f, if and only if, you can find a finite number of algebraic elements so that k is just f attached those algebraic elements. So a finite extension is all finite extensions are obtained just by attaching a finite number of algebraic elements. That's how you get all finite extensions. All right, start with number 1. Start with an element alpha and k. We want to show that alpha is actually algebraic over f, and then that will say that k is an algebraic extension. All right, well, since this degree here is finite, and the degree of f of alpha over f divides it, this thing too is finite, and so the previous lemma says that actually is alpha is algebraic. All right, let's turn to part 2 and let's go to the left. All right, well, start with this usual chain of subfields. F contained in f, attach alpha 1. And then to that, attach alpha 2. So that's f of alpha 1, attach f alpha 2, which is the same as just f of adjoin alpha 1, alpha 2. Then attach alpha 3, and so on until you get to k. Now, since alpha 1 is algebraic, that means that this is a finite extension. And then, in the next step, alpha 2 is actually a finite, Alpha 2 is algebraic over f, so it's certainly algebraic over f of attach alpha 1. You can kill it with polynomials just in f. You might be able to kill it even faster with coefficients in f attach alpha 1, but this will be finite. And for the same reason, when you attach alpha 3, it's algebraic over the base field f, so it's certainly algebraic over this intermediate field, so that's a finite extension. And then you just use the multiplication of degrees to get that the whole thing will be finite, since every single piece is. And the total degree of k over f will just be the product of all these numbers, and so that'll be finite. Okay, the last part. Okay, we're just going to kind of construct these alphas. So if k were f, then there's nothing to do. So suppose k is not f, and then since that's the case, that means there's some alpha 1 that's in k but not in f. So grab that one. By the fact that the degree of k over f is finite, then the degree of each of these pieces is finite. So in particular, this degree has to be finite, and so alpha 1 is algebraic over f. I also want to remark that since alpha 1 is not in f, then the degree of f attach alpha 1 over f has to be at least 2. It can't be 1, or else these two fields would be the same thing, and alpha 1 would be in f. Okay. All right. If k is equal to f of alpha 1, we're done. Otherwise, pick an alpha 2 that's in k but not in f of alpha 1. And with that same type of chain of ideals, f of alpha 1 contained in f of alpha 1 attached alpha 2 contained in k, you see that alpha 2 is algebraic. And in fact, since alpha 2 is not in f of alpha 1, the degree of f of alpha 1, 2 over f alpha 1 is at least 2. All right, now you just repeat. You've got f contained in f of alpha 1, and then if you're not done, you attach an alpha 2, and if you're not done, you attach an alpha 3. And each time, as we said, this degree from here to here was at least 2, and this degree extension was at least 2, and if you keep doing this degree will be at least 2, and so on. And the result is the dimension of this, of k over f, is going up at least by multiples of 2 every time you do this. Therefore, since it's a finite extension, you can't do this forever. Eventually, this process has to stop, and you get to a point when you attach an element and you have to get all of k. And at that point, you're done. So that's the end of that proof. Okay, now we've got a fun little corollary. I remember this corollary, actually, when I first read from an algebra book, and it's easy now, but it always seemed very surprising to me. So here it is. So here's the statement. If you've got f contained in k and you've got two fields, you've got two elements, alpha and beta, and they're both algebraic over f, then so is their sum, their difference, their product, and their quotient. In other words, if you do anything algebraic with algebraic elements, they stay algebraic. All right, so as usual, chain of subfields. F attach alpha, and you can view it as a field or as a ring, same thing. And then you attach beta, you could view it as a field or ring because they're algebraic. And since each step is algebraic, there's finite degrees here. And since degrees are multiplicative, then this is finite. So the point is, this whole extension, since it's finite, is actually algebraic. And all these elements are in this field extension, and therefore they're all algebraic. And so that's the end of the proof. Here's an example. All right, fifth root of 2, algebraic. Ninth root of 8, algebraic over Q. 71st root of 16, algebraic over Q. Therefore, all combinations, sums and quotients and division keeps it algebraic. So this element here is actually algebraic over Q. And at first, that seems kind of hard. How do you come up with a polynomial? But anyway, that's that. End of the section.